You are listening to Event-Driven Architecture, a practical guide to building scalable, resilient, and responsive systems. Like and subscribe to keep up to date on our latest audiobooks. Event-Driven Architecture, a practical guide to building scalable, resilient, and responsive systems. The Asynchronous World, Why Event-Driven Architecture, Introduction. The Shifting Sands of Modern Systems. Imagine a world where your favorite online retailers can instantly track your package's journey, your smart home devices react seamlessly to your presence, and financial transactions process in mere milliseconds, even under immense global demand. This isn't science fiction, it's the expectation of modern digital life. But behind these seemingly effortless experiences lies a monumental shift in how software systems are built. For decades, the standard approach was often synchronous. Think of it like a chain of phone calls. Service A calls Service B, waits for B to complete its task, and only then can it continue. This worked well for simpler applications, often built as massive monoliths, single, tightly integrated codebases. However, as user demands grew, as businesses needed to scale instantly, embrace cloud computing, and react to real-time data, these traditional architectures started to creak under the strain. They became rigid, difficult to change, prone to cascading failures, and challenging to scale effectively. This led to the rise of distributed systems, notably microservices, where large applications are broken down into smaller, independent services. But how do these independent services talk to each other without recreating the old synchronous bottlenecks? How do you ensure that if one part of the system fails, the entire house doesn't come crashing down? The answer, increasingly, lies in a powerful paradigm called event-driven architecture, or EDA. What does event-driven even mean? At its heart, event-driven architecture is remarkably simple. Systems react to events. An event is merely a significant occurrence or a factual record of something that has already happened within your business domain. It's a notification, a time-stamped declaration of a change in state or activity. To understand this, let's use an analogy. Imagine you're running a bustling factory that manufactures custom bicycles. In a traditional, synchronous phone call model, a customer placing an order would trigger a direct call from the sales department to the factory floor. The salesperson would wait on hold while the factory checked inventory, assembled the bike, and then called back with a confirmation. If the factory was busy, the salesperson would be stuck, unable to take new orders. If the phone line disconnected, the entire process might halt. Now, picture an event-driven factory. When a customer places an order, the sales department doesn't make a direct call. Instead, they simply publish an order-placed event. This event is like a sticky note placed on a central, visible whiteboard. Order 123 placed for a red mountain bike. They don't wait for confirmation, they immediately move on to the next customer. Many other departments are constantly watching this whiteboard. The inventory department sees Order 123 placed, and they independently go check stock. If a part is low, they might write a low stock alert event. The assembly department sees Order 123 placed and starts preparing their tools. The shipping department sees bike assembled and prepares a delivery label. Each department reacts independently to the events on the whiteboard without needing to directly coordinate or wait for others. This whiteboard, a central point where events are published and consumed, is a simple analogy for an event broker, which we'll cover in detail soon. The key idea is that the sales department doesn't command the factory. It simply informs it that something has happened. The factory and other departments then reacts on its own schedule. Events, therefore, are not commands, do this. They are facts, this happened. This subtle but profound shift from imperative commands to declarative facts is the cornerstone of EDA. The promise of event-driven architecture, why bother? This reactive, asynchronous approach unlocks a multitude of benefits for modern software systems. Decoupling, this is perhaps the most significant advantage. In our factory analogy, the sales department doesn't know or need to know how the factory works, what its internal processes are, or even if it's currently busy. It only knows how to publish an order-placed event. Similarly, the factory doesn't care who placed the order, it just reacts to the event. Practical benefit: Services become independent. You can develop, deploy, and scale them in isolation, minimizing dependencies and reducing the ripple effect of changes or failures. Adding a new feature, like a loyalty point system, might simply mean creating a new service that subscribes to order-placed events without touching or even redeploying the existing sales or factory services. Scalability: when components are decoupled, they can scale independently. If order placement spikes during a sale, you can add more sales desks, producer instances. If the shipping department falls behind, you can add more shipping clerks, consumer instances without affecting order placement or assembly. Practical benefit: systems can handle sudden bursts of activity gracefully. You're not limited by the slowest part of a synchronous chain. Resilience and fault tolerance: what happens if the assembly department in our synchronized factory goes on break or encounters a problem? The entire production line stops. In our event-driven factory, if the assembly department goes down, new order-placed events simply pile up on the whiteboard. When assembly comes back online, they pick up exactly where they left off, processing the backlog. Practical benefit: a failure in one service doesn't necessarily bring down the entire system. Events can be buffered and reprocessed, leading to much more robust and self-healing applications. Agility and extensibility: because systems react to facts rather than direct commands, adding new functionality often means simply introducing a new event consumer. Imagine adding a new customer feedback department to our bicycle factory. They just need to start watching the order-delivered events to send out survey requests. They don't need the sales team or assembly team to change their processes. Practical benefit: new features can be rolled out faster and with less risk, fostering innovation and quicker adaptation to market changes. Responsiveness: for crucial customer-facing interactions, EDA can provide immediate feedback. When you click Place Order online, the system can quickly acknowledge your order, "Thank you," by promptly publishing an order-initiated event, even if the complex chain of fulfillment, payment processing, inventory allocation, shipping happens asynchronously in the background. Practical benefit: improves user experience by giving instant confirmation while allowing intensive background tasks to run without blocking the user interface. Beyond the hype: common misconceptions and initial considerations. While the benefits are compelling, it's crucial to acknowledge that event-driven architecture isn't a silver bullet. It's not suitable for every problem, and it introduces its own set of challenges. The complexity doesn't disappear, it often shifts. For instance, achieving immediate data consistency across different services can be more challenging than in a monolithic, synchronously updated database, a concept known as eventual consistency that we will explore. Adopting EDA also requires a different way of thinking about system design. Developers and architects must learn to conceptualize processes as sequences of immutable events rather than direct calls. It's a mind shift from, "I call you to do this," to "I announce that this happened," and others interested can react. It changes how you model business processes, how you debug issues across distributed systems, and even how teams within an organization collaborate. Furthermore, while the idea of a simple whiteboard is appealing, the underlying technologies that reliably and securely manage events can be complex to set up and operate at scale. We'll touch upon these considerations as we delve deeper. Setting the stage: throughout this book, we will demystify event-driven architecture. We'll start by diving deeper into the anatomy of an event, then explore the core components that make these systems tick: event producers, consumers, and the critical role of event brokers. We'll then delve into powerful design patterns like Event Sourcing and CQRS, tackle the complexities of consistency and error handling in a distributed context, and discuss real-world applications where EDA truly shines. Finally, we'll offer guidance on how to adopt EDA, both from a technical and organizational perspective. Prepare to embark on a journey into the asynchronous world, where systems are not just faster, more scalable, and more resilient, but fundamentally more adaptable to the ever-changing demands of the digital age. Anatomy of an event: the building blocks of EDA. Introduction: the unsung hero of modern systems. In the previous chapter, we established that event-driven architecture, EDA, centers around the concept of events. We use the analogy of a busy factory where departments react to notes on a whiteboard rather than direct instructions, highlighting the benefits of this asynchronous, decoupled approach. But what exactly is an event in the context of software? What makes it special, and why is understanding its nature so crucial to building successful event-driven systems? Simply put, events are the factual building blocks upon which an EDA system is constructed. They are the language through which independent services communicate, the records that drive business processes, and the historical ledger of everything significant that has occurred. Without a clear understanding of what an event entails, the entire architecture becomes difficult to manage, debug, and evolve. What constitutes an event? An event, as we define it in EDA, is an indelible record of something that has occurred. It's a notification of a state change or an occurrence of significance within a system or business domain. Crucially, an event represents a past tense fact, a finished action. Let's break down the key characteristics that define a true event. Immutability. Once an event has happened and been captured, its content cannot be changed. It's a historical fact, like a receipt for a purchase or a time-stamped log entry. You wouldn't go back and change what was on a receipt after a transaction. And similarly, you don't alter an event. If new information arises or a change needs to be made, a new event is generated to reflect that subsequent occurrence. For example, if an order-placed event is recorded and then the customer decides to cancel, a new order-canceled event is published, rather than modifying the original order-placed event. Factuality. An event describes what happened, not what to do. An user-registered event states that a user has successfully registered. It doesn't instruct a service to register a user. This distinction is critical because consumers of an event decide how they will react to that fact. The inherent factuality of events allows different parts of your system to interpret and react to the same occurrence in different ways, without needing prior coordination. Timestamped. Every event must carry a timestamp indicating when it occurred. This is fundamental for several reasons. It allows services to process events in chronological order, helps with debugging, supports auditing, and enables analysis of temporal patterns, e.g., how long does it take from order placement to shipping? Contextual. An event needs to contain enough information for a consumer to understand what happened without needing to query other services. It should carry all the necessary data points relevant to that specific occurrence at that specific point in time. For instance, an order-placed event would contain the order ID, customer ID, total amount, list of items, and possibly the shipping address. It shouldn't contain the customer's entire profile, but enough context related to the order itself. Idempotency, consumer side. While an event itself is immutable, it's vital that the processing of an event by a consumer is idempotent. This means that if a consumer receives and processes the same event multiple times, it should produce the exact same result and not cause undesirable side effects. This property is crucial in distributed systems where network issues or retries might lead to duplicate event deliveries. For example, if a consumer processes an account-credited event twice, the account should only be credited once. We'll delve deeper into how to achieve idempotency in later chapters. The structure of an event, what's inside. While an event's exact structure can vary, most share common conceptual components. Metadata. This is the envelope information about the event itself, not necessarily about the business data it carries. Event ID. A unique identifier for this specific instance of the event. This is critical for tracing, debugging, and achieving idempotency. Timestamp, the precise time the event occurred. Event type, a clear, concise name describing what happened, e.g., order placed, payment accepted, user logged in. This is how consumers know what kind of event they are receiving. Source, which system or service generated this event. Version, an indicator for the event's schema version. As systems evolve, the structure of events might change. Versioning allows consumers to understand how to interpret an event, even if it was published using an older or newer schema. Payload data. This is the actual business data pertinent to the occurrence. It contains the contextual information needed for consumers to react. For an order-placed event, the payload would include details like order-id, customer-id, total amount and currency, items, a list of products, quantities, prices, delivery address, any other data relevant at the moment the order was placed. Think of an event like a meticulously prepared shipping label on a package. The metadata is like the routing details on the label: tracking number, event ID, shipping date, timestamp, contents type, event type, sender, source, etc. The payload is not the entire contents of the box, but rather the essential descriptive information about the contents, e.g., 3x red widgets, 1x blue gadget, that a shipper or receiver needs to understand the package's purpose without opening it. Types of events, a taxonomy. While all events share fundamental characteristics, it's often helpful to categorize them based on their scope and purpose. Domain events. These events signify something important that has happened within a single business domain or bounded context. They are primarily used for internal communication between components or aggregates within that domain. For example, within an e-commerce order domain, events like item added to cart, payment attempted, or order line updated would be domain events. They reflect granular changes that, when aggregated, constitute the full story of an order. Integration events. These events are published specifically to communicate significant changes across service boundaries or to external systems. They integrate different parts of a larger enterprise or even different organizations. Often, an integration event is a summary of one or more domain events. For example, once an order is fully processed internally, the order service might publish an order-placed integration event to notify the shipping service, the inventory service, and the customer communication service that a new order needs attention. These services don't need all the granular domain events that led to the order-placed event. They just need the final, significant fact. The distinction between domain and integration events is sometimes fluid and depends on the architectural design choices. However, generally, integration events are coarser-grained and carry less detail than the underlying domain events, as they are meant to inform other independent systems, not to replay the exact sequence of internal actions. Event granularity. How big or small should an event be? One of the common design dilemmas in EDA is determining the appropriate level of detail, or granularity, for your events. Fine-grained events describe very small changes, e.g., unit price changed. This can lead to a large number of events, each with a small payload. While this captures every detail, it can make it harder for consumers to understand the overall picture without combining many events. Coarse-grained events describe larger, more significant changes, e.g., order updated. This reduces the number of events, but means each event carries a larger payload and might abstract away some details. The general guidance is that an event should represent a single, atomic fact. If an event can be logically broken down further into multiple independent facts, it probably should be. For example, instead of a generic order-changed event with a large payload that indicates multiple fields updated, it's often better to have more specific events like shipping address changed and payment method updated. This makes events clearer, easier to consume, and more aligned with the principle of immutability of specific facts. It also supports better forward compatibility, as consumers only need to subscribe to the specific changes they care about. The importance of event naming and schema. Just like variables and functions in programming, how you name your events is critical for clarity and maintainability. Clear naming. Event names should be descriptive, unambiguous, and consistently follow a convention. A widely accepted convention is to name events in the past tense, reflecting their "this happened" nature, e.g., user registered, product published, invoice paid. Avoid generic names like data changed or active verb names like update order, as they violate the factuality principle. Clear names simplify understanding for anyone viewing the event stream. Schema definition. The structure of an event's payload, its schema, should be explicitly defined and versioned. This provides a contract between producers and consumers. If a producer changes the structure of an event, e.g., adding a new field, it should ideally either publish a new version of the event or ensure backward compatibility. Tools and standards like JSON schema, Apache Avro, or protocol buffers are often used to define and enforce event schemas. ensuring that consumers can reliably parse and interpret the data they receive. While we won't delve into the specifics of these technologies here, understanding the need for machine-readable schema definition is paramount for building robust and evolvable event-driven systems. What an event is not. To further solidify our understanding, it's helpful to clarify what an event is not. Not a command. A command is an instruction or a request for a service to do something, e.g., register user, process payment. Commands are imperative and imply an expectation of a specific action. Events, contrastingly, are declarative and simply state something that has already finished. Not a query. A query is a request for information, e.g., get user BID, get order details. Queries aim to retrieve the current state. Events are about past state changes, not a volatile data stream. While events can feed real-time data streams, the event itself is a discrete, immutable record of a specific occurrence, not a continuous flow of raw data points. Not a database change log, necessarily. While a database change log certainly reflects events in a low-level sense, e.g., row inserted, column updated, an event-driven architecture typically focuses on higher-level business events that represent meaningful domain occurrences, not just technical database operations. Conclusion: events as the language of your business. Events are more than just data structures. They are the fundamental language through which your business processes communicate and evolve. By understanding and carefully designing the anatomy of your events, their immutability, factuality, inherent context, and clear structure, you lay a robust foundation for an event-driven architecture. These well-defined events become the atomic units of information that drive every subsequent action in your system, enabling the decoupling, scalability, and resilience we discussed in the first chapter. In the next chapter, we will introduce the key architectural components that bring these events to life, forming the channels through which facts are communicated and reactions are orchestrated. Core components: producers, consumers, and event brokers. Introduction: the cast of characters in an event-driven play. In the previous chapters, we've established the why of event-driven architecture and meticulously examined the what of an event, an immutable, factual record of a significant occurrence. But how do these events actually move through a system? Who creates them? Who receives them? And how are they reliably transmitted from one place to another? Just like a theatrical play needs its actors and a director to bring a story to life, an event-driven system relies on a specific cast of components, each with a defined role. These components interact seamlessly to ensure that events flow efficiently, allowing independent parts of your system to react to changes as they happen. At their core, these roles boil down to three main characters: event producers, event consumers, and the crucial intermediary, the event broker. Understanding the responsibilities and interactions of these three will unlock your ability to design robust and responsive event-driven systems. Event producers, the senders of truth. Let's begin with the originators of information in an EDA system. Definition: an event producer, sometimes called an event publisher or emitter, is any system, service, or component that detects a significant occurrence within its domain and subsequently generates and publishes an event to notify the rest of the system. Responsibilities: detecting occurrences. Producers are on the front lines, constantly monitoring for changes or actions that warrant an event. This could be a user clicking a place order button, a sensor recording a temperature spike, or a payment gateway confirming a transaction. Constructing events. Once an occurrence is detected, the producer is responsible for packaging that information into a properly structured event. This means ensuring the event has all the necessary metadata, ID, timestamp, type, source, and a relevant payload of data, as discussed in Chapter 2. Publishing events. The producer then sends this newly constructed event to an event broker. Crucially, the producer does not concern itself with who will receive or act upon this event. Its job is simply to announce the fact and make it available. Characteristics: decoupled from consumers, a producer operates completely independently of its consumers. It doesn't know how many consumers there are, what they do with the event, or even if they are currently online. This fundamental separation is a cornerstone of EDA's flexibility. often stateless regarding event production. While the underlying service producing the event might have its own state, e.g., an order service managing order state, the act of producing an event is often stateless. It simply observes a change and announces it. Example: in our e-commerce scenario, when a customer successfully completes checkout, the order service acts as an event producer. It processes the order, updates its internal state, and then publishes an order-placed event to an event broker. Its task is complete. It doesn't wait for internal confirmations from inventory or shipping. Event consumers, the listeners and reactors, on the other side of the event flow, are the components that actually do the work based on what has happened. Definition: an event consumer, also known as an event subscriber or handler, is any system, service, or component that expresses interest in specific types of events, receives them from an event broker, and then performs its designated business logic in response. Responsibilities: subscribing to events, consumers register with the event broker, indicating which types of events they wish to receive. Receiving and interpreting events: upon receiving an event, the consumer parses its content and understands the factual occurrence it represents. Performing business logic: this is where the reactiveness of EDA comes into play. Based on the event, the consumer executes its specific task. This could involve updating a database, sending an email, triggering another process, or even publishing a new event. Acknowledging processing: after successfully processing an event, the consumer typically sends an acknowledgement back to the broker, indicating that the event has been handled and can be removed from its queue or marked as processed. This is vital for reliable delivery. Handling errors gracefully: consumers must be designed to cope with situations where processing fails. This might involve retrying the operation, logging the error, or moving the problematic event to a dead-letter queue for manual intervention. Characteristics: idempotency is crucial. As mentioned in Chapter 2, consumers must be designed to process the same event multiple times without undesired side effects. In distributed systems, network issues or broker retries can sometimes lead to an event being delivered more than once. An idempotent consumer ensures that if it receives the same account-credited event twice, the account is only credited once. Highly decoupled from producers: just as producers don't know their consumers, consumers don't know their producers. They simply react to the event, regardless of its origin. Can be stateful or stateless. A consumer might be stateless, e.g., an email sender, or maintain its own internal state, updating it based on events, e.g., a service building a personalized user profile from activity events. Example: after the order service publishes an order-placed event, several consumers might react. The customer notification service: Consumer 1 subscribes to order-placed events to send a confirmation email or SMS to the customer. The inventory service: Consumer 2 subscribes to order-placed events to reduce stock levels for the ordered items. The shipping service: Consumer 3 subscribes to order-placed events to initiate the shipping process. Each consumer performs its task independently, notified by the same single event. The event broker, the central nervous system: the magic of decoupling between producers and consumers wouldn't be possible without a reliable intermediary to manage the flow of events. This is the role of the event broker. Definition: an event broker, often referred to as a message broker, message queue, or event bus, is a specialized system that receives events from producers and reliably delivers them to interested consumers. It acts as a buffer and an intelligent communication hub. Key functions: buffering: brokers temporarily store events until consumers are ready to process them. This prevents producers from being blocked if consumers are slow or temporarily offline. It also handles peaks in event volume. Routing and publish subscribe: the broker allows producers to simply publish events to a named channel or topic without explicitly knowing who will consume them. Consumers, in turn, can subscribe to specific topics, ensuring they only receive the events relevant to their function. Think of it like a newspaper publisher, producer, printing articles to a specific section topic, and subscribers, consumers, choosing which sections they want to receive. Durability and persistence: A robust event broker ensures that events are not lost, even if the broker itself or its connected producers, consumers experience failures. Events are persisted to disk until they are successfully processed by their intended consumers. Scalability. Modern event brokers are designed to handle immense volumes of events, often in the order of millions of events per second, without becoming a bottleneck. They can distribute the load across multiple servers. Ordering, optional, but important. While not universal, many brokers offer guarantees about the order of events within a specific partition or stream. This is crucial for scenarios where the sequence of events matters, e.g., balance credited must happen before balance debited. Different implementations, conceptual, queues, point-to-point. In a traditional message queue model, an event is sent to a queue, and typically only one consumer retrieves and processes that event. Once processed, it's removed from the queue. This is good for distributing workload among a group of identical consumers, e.g., a pool of image processing workers. Topics, publish-subscribe. In a publish-subscribe model, an event is published to a topic, and multiple consumers can subscribe to that topic, each receiving a copy of the event. This is ideal for broadcasting events to many different services that need to react independently, as in our order-placed example. Most modern event brokers, such as Apache Kafka, Amazon SQS SNS, RabbitMQ, or Google Cloud PubSub, offer combinations of these capabilities, providing flexible options for different communication patterns. They manage the complex logistics of event delivery, retries, and persistence, freeing producers and consumers to focus on their core business logic. Putting it all together. The event flow. Let's revisit our order-placed scenario and trace the event's journey through these components. Customer action. A customer completes their purchase on the e-commerce website. Producer generates event. The order service. An event producer detects the successful order. It constructs an order-placed event containing all relevant order details. Producer publishes to broker. The order service publishes this order-placed event to a designated order events topic on the event broker. It's done with its part. It doesn't wait for anything. Broker stores and distributes. The event broker receives the event, stores it durably, and identifies all services that have subscribed to the order events topic. Consumers receive event. The customer notification service, inventory service, and shipping service, all event consumers, having previously subscribed to this topic, each receive a copy of the order-placed event from the broker. Consumers process independently. The customer notification service processes the event to send a confirmation email. The inventory service processes the event to decrement stock levels. The shipping service processes the event to add the order to its shipping queue. Consumers acknowledge. Each consumer, upon successful completion of its task, sends an acknowledgement back to the broker. This entire process occurs asynchronously, often within milliseconds, showcasing the power of decoupling. Beyond the basics, event stores, brief introduction. While event brokers are crucial for transient event delivery, some event-driven architectures also incorporate a concept known as an event store. Definition: an event store is a specialized database that stores a complete, immutable, ordered sequence of all events that have ever happened in a system or specific domain. Distinction: unlike a traditional operational database that stores the current state of entities, e.g., the current balance of an account, an event store stores the history of how that state was arrived at, e.g., deposit received, withdrawal made. The current state can then be derived by replaying all relevant events from the beginning of time. This powerful concept, known as event sourcing, forms the basis for complex auditing, historical analysis, and certain advanced architectural patterns. We will delve deeply into event sourcing and the role of event stores in Chapter 5. For now, understand them as a potential, but not mandatory, component in a sophisticated event-driven system, distinct from the primary role of an event broker for real-time message passing. Conclusion: building blocks for dynamic systems. Event producers, event consumers, and event brokers are the foundational elements for designing and implementing event-driven systems. They collectively enable the asynchronous, decoupled, scalable, resilient, and agile properties that make EDA so compelling for modern software. Understanding their individual responsibilities and their coordinated dance is key to harnessing the full power of events. In the next chapter, we will build upon this foundation by exploring common design patterns and communication styles enabled by these core components, specifically examining the crucial distinction between choreography and orchestration in event-driven flows. Designing for decoupling, choreography vs orchestration. Introduction: the challenge of coordination in a decoupled world. In the prior chapters, we explored why event-driven architecture, EDA, is valuable and what an event fundamentally is. We then detailed the essential components producers, consumers, and the event broker that enable events to flow through a system. The primary benefit we highlighted was decoupling, the ability for services to operate independently without direct knowledge of each other, allowing for greater agility, scalability, and resilience. However, a critical question quickly arises. If services are truly independent and only react to events, how do they collectively achieve a larger, multi-step business goal? How does placing an order eventually lead to shipping, invoicing, and inventory updates, all while maintaining a coherent overall process? The answer lies in how these independent services coordinate their actions. In EDA, there are two predominant patterns for achieving this coordination: choreography and orchestration. Each offers a different philosophy for managing the flow of activity, with distinct advantages and disadvantages relative to the degree of decoupling they provide. Choreography: the decentralized dance. Imagine a magnificent human flash mob. There's no single leader standing on a podium shouting instructions. Instead, each participant knows their specific dance moves and when to execute them based on cues from the people around them. As one group transitions from a wave to a jump, the next group immediately picks up their synchronized routine. The entire spectacle unfolds without explicit central direction. This is the essence of choreography in an event-driven system. Definition: in a choreographed system, each service is aware of its own role and reacts directly to events published by other services. There is no central coordinator. Each service publishes an event indicating that it has completed its part of a process, and interested services then subscribe to those events and react accordingly. The overall business process flow emerges from the independent reactions of individual services. How it works: Service A completes a task and publishes Event X. Service B and Service C are subscribed to Event X. Service B receives Event X, performs its task, and publishes Event Y. Service D is subscribed to Event Y, and so on. The process unfolds like a chain reaction, driven by the events themselves. Pros: maximum decoupling. This is the pinnacle of independence. Services have minimal knowledge of each other's existence, needing only to agree on the format of the events they publish and consume. This allows for truly independent development, deployment, and scaling. Flexibility and agility. Adding a new step to a business process often means simply adding a new consumer that subscribes to an existing event. No modification to existing services is needed. For example, if you want to add a loyalty point system, you just create a new service that reacts to the order-placed event. Resilience. Since there's no central point of control, the failure of one service doesn't necessarily halt the entire process. Events can be retried or processed later, allowing the rest of the system to continue functioning. Cons: lack of central visibility. It can be challenging to understand the entire end-to-end business process. The overall flow is scattered across multiple services, making it difficult to visualize, debug, or audit what happened where when things go wrong. This is sometimes jokingly referred to as spaghetti events if poorly designed. Implicit logic. The business process logic is implicitly embedded within each service's reaction to events. This can make it harder to change complex business rules that span multiple services. Debugging challenges. Tracing a specific business transaction through a series of chained events across different services can be complex, often requiring sophisticated distributed tracing tools. When to use. Choreography shines in simpler, less complex business processes or processes where high decoupling is paramount. It's often favored when the participants in the flow are stable, well-defined, and their interactions are relatively straightforward. For example, a basic e-commerce order fulfillment, order placed, inventory updated, shipping initiated, email sent, is a strong candidate. Orchestration, the centralized conductor. Now, contrast that with a classical orchestra. There's a conductor at the front, a single point of control, who interprets the score and provides explicit commands to each section: strings, woodwinds, brass, percussion. The conductor knows the entire piece, when each instrument should play, and how they contribute to the overall symphony. This is orchestration in an event-driven system. Definition: in an orchestrated system, a dedicated orchestrator service, sometimes called a saga orchestrator or workflow engine, manages the progression of a multi-step business process. This orchestrator service holds the entire business process logic and explicitly tells other services what to do, often using commands, requests to perform an action, rather than just reacting to events. How it works. An initiating event, e.g., order requested, is received by the orchestrator. The orchestrator sends a command A to service A, e.g., process payment. Service A processes the command and responds with an event, e.g., payment processed or payment failed. The orchestrator receives this event, updates its internal state of the process, and based on the outcome, sends command B to service B, e.g., reserve inventory, or initiates a compensation flow. And so on, until the entire business process is complete or an error is handled. Pros: clear visibility. The entire flow of a business process is defined and managed in one concise place, the orchestrator service. This makes it far easier to understand, debug, and audit the end-to-end process. Controlled process. Orchestrators excel at enforcing precise business rules, managing complex conditional logic, and handling error scenarios, e.g., retries, timeouts, or compensating transactions that roll back previous steps. If a step fails, the orchestrator knows the exact state and can trigger predefined recovery actions. Explicit flow. The sequence of steps and dependencies is explicit and centralized. Cons: reduced decoupling. The orchestrator becomes a central dependency. While you still have service independence, the orchestrator inherently introduces some coupling to the services it orchestrates, as it needs to know their interfaces and expected responses. It also becomes a potential single point of failure, though this can be mitigated with robust design. Scalability concerns. The orchestrator itself can become a bottleneck if not designed to handle a high volume of concurrent workflows. Less agile. Changes to the overall business process, logic, often require modifying and redeploying the orchestrator service, which can impact agility compared to simply adding a new choreographic consumer. When to use. Orchestration is often favored for complex, long-running business processes that span multiple services, especially those requiring strict sequencing, complex conditional logic, or sophisticated error handling and compensation. A multi-step loan application process involving credit checks, risk assessment, and approval is a classic example where an orchestrator might be beneficial. This pattern is also closely related to saga patterns, which address distributed transactions and consistency, a topic we will delve into in more detail in Chapter 5. Choosing your approach, when to choreograph, when to orchestrate, there is no universally better approach. Both choreography and orchestration have their strengths and weaknesses, making them suitable for different scenarios. In many real-world systems, you'll find a pragmatic blend of both. Here are factors to consider when deciding which pattern to adopt. Complexity of the business process. Choreography. Ideal for simple, fire-and-forget reactions or clear, short-lived sequential flows with minimal error handling complexity. Orchestration. Better suited for complex, long-running business processes that involve conditional logic, multiple decision points, and sophisticated error recovery. Need for central visibility. If understanding and debugging the complete end-to-end flow is paramount, orchestration provides that centralized view. If services primarily act independently and the overall flow is less critical to monitor as a single unit, choreography is sufficient. Degree of decoupling required. If maximum autonomy and independent deployment of all services are your top priorities, choreography moves you closer to that ideal. If you're willing to accept a degree of centralized control for the benefits of explicit flow management and error handling, orchestration is a valid compromise. Error handling complexity. In choreography, error handling is distributed. Each service is responsible for its own retries or reporting failures. Compensating for errors across multiple services can be very complex with choreography, requiring a complex chain of undue events. Orchestration provides a single point to manage complex error flows, including retries, timeouts, and ensuring compensatory actions are taken across multiple services if a process fails midway. Team structure. Choreography often aligns well with independent, autonomous teams, where each team owns a service and its reactions. Orchestration might suit a team that focuses on defining and managing complex business workflows across multiple existing services. As a general guideline, start with choreography whenever possible. It's often simpler to implement initially and maximizes decoupling. Only introduce an orchestrator when the decentralized nature of choreography leads to significant pain points, such as difficulty in understanding the overall flow, managing complex business rules spanning multiple services, or providing robust error handling for critical, long-running processes. Avoid the temptation to build smart orchestrators that embed too much business logic, making the other services dumb and merely executors of the orchestrator's will. Aim for smart services dumb pipes, whether the pipe is a direct event or an orchestrator mediating commands. Conclusion: balancing autonomy and coordination. Both choreography and orchestration are powerful patterns for coordinating actions in an event-driven architecture. Choreography prioritizes ultimate decoupling and flexibility, allowing an emergent flow, while orchestration offers centralized control and explicit visibility, which is invaluable for complex business processes and sophisticated error management. The choice between them, or often the strategic combination of both, reflects a fundamental architectural trade-off. It's about balancing the autonomy of individual services with the need for coherent, measurable, and reliable execution of end-to-end business workflows. Understanding this balance is a crucial step in designing effective event-driven systems. In the next chapter, we will build on these coordination patterns by exploring advanced patterns like event sourcing and CQRS, which fundamentally change how data is stored and queried in an event-driven world. Advanced patterns, event sourcing, CQRS, and sagas. Introduction: elevating event-driven design. We've laid the groundwork for understanding event-driven architecture, EDA. The fundamental why, the structural what of events, and the basic components producers, consumers, and brokers that facilitate event flow. We then explored the critical coordination patterns of choreography and orchestration. Now we ascend to a higher level of design, delving into advanced patterns that often accompany and significantly enhance EDA, particularly when dealing with complex data management, auditing, and maintaining consistency across distributed systems. This chapter will introduce three powerful patterns: event sourcing ease, command query responsibility segregation, CQRS, and sagas. While each can stand on its own, they are frequently used in combination, especially ease and CQRS, to unlock new capabilities and tackle some of the most challenging aspects of distributed system design. They represent a philosophical shift, pushing the boundaries of what is possible with events as the central truth. Event sourcing, the ledger of truth. Imagine a traditional accounting system. You don't just store a bank balance. You store every single transaction that led to that balance: deposits, withdrawals, transfers, payments. If you want to know the balance at any point in history, you simply sum up the transactions up to that date. Event sourcing applies this exact principle to your application's data. Definition: event sourcing is an architectural pattern where the state of an application or a business entity is not stored directly, but rather as a sequence of immutable events that represent every change to that state. Instead of saving the current snapshot, you save the history of how that snapshot came to be, how it works. When a change occurs, e.g., a customer places an order, an item is added to a cart. An event representing that change is created. This event is then stored in an event store, a specialized, append-only database optimized for storing sequences of events. It's essentially a chronological ledger of everything that has ever happened in your system. The current state of an entity, e.g., an order, a customer account, is reconstructed by replaying all the events related to that entity from the beginning of its history. Benefits: complete audit trail and history. You have a perfect, immutable record of every single action that occurred, allowing for rich auditing, compliance, and debugging. You can time travel to any point in the past by replaying events up to that specific timestamp. Resilience and disaster recovery. Since state is derived from events, if your application's operational database is lost, you can rebuild the entire application's state by replaying all events from the event store. Facilitates debugging. When debugging a bug related to state, you can examine the exact sequence of events that led to the erroneous state. Enables advanced analytics. The rich history of events provides a powerful source for business intelligence, machine learning, and understanding user behavior patterns. Foundation for other patterns. Event sourcing is often the springboard for patterns like CQRS and sagas. Challenges: complexity of querying current state. Directly querying for the current state can be computationally expensive since it requires replaying events. Event versioning and schema evolution. As your application evolves, the structure of your events might change. Managing how older events are interpreted by newer code is a significant challenge. Data volume. Over time, the event store can grow very large, though modern solutions are designed to handle this. Read model necessity. For efficient querying, a separate read model is almost always required, leading us to CQRS. Command Query Responsibility Segregation, CQRS, optimizing reads and writes. When event sourcing is employed, accessing the current state of an entity usually involves processing a stream of events. While powerful for auditing and historical analysis, this approach is typically inefficient for everyday retrieval of an entity's current state, especially for complex queries or high-volume reads. This is where CQRS comes into play. Definition: CQRS is an architectural pattern that separates the concern of commands, which change state, from queries, which read state. Instead of a single data model or database serving both writes and reads, CQRS uses distinct models, often backed by distinct data stores, optimized for their specific purpose. Why it's often used with event sourcing. With event sourcing, the write-side command model inherently deals with events and the event store. The read-side query model then needs a way to efficiently serve the current state. How it works with event sourcing. Command model write-side receives commands, instructions to change state, e.g., place order. Validates the command. Loads the current state of the affected entity from the event store by replaying events or from a cached snapshot. Applies the change, generating one or more new events. Persists these new events to the event store. Query model read side. Events from the event store are asynchronously published, e.g., via the event broker, to projection or read model services. These services consume the events and update purpose-built data stores, e.g., a NoSQL database for flexible querying, a relational database for rich reporting, or a search index like Elasticsearch, with the current state of entities. Queries, requests for information, e.g., get order details, are then directly served from these optimized read models. Benefits: scalability. The read and write workloads can be scaled independently as they use separate resources. This is crucial for applications with high read-to-write ratios. Optimized queries. Read models can be tailored precisely to the querying needs, using the most appropriate database technology, e.g., graph databases for relationships, search engines for full-text search, and schemas. Flexibility and evolution. Read models can be easily rebuilt or created anew from the historical event stream in the event store, supporting changes in reporting or UI requirements without affecting the core write logic. Separation of concerns. Clearer separation of business logic for state changes versus data retrieval. Challenges: eventual consistency. The read model updates asynchronously from the write model. This means that immediately after a command is processed, the read model might not yet reflect the very latest state. For some applications, this eventual consistency is acceptable. For others, it requires careful handling, e.g., displaying an order pending status until the read model catches up. Increased complexity. CQRS adds more moving parts, including multiple data stores, replication mechanisms, and event processing pipelines. Debugging and monitoring. Tracing data flow across distinct read and write models requires more sophisticated tooling. Sagas, managing distributed transactions. In distributed systems, a single business operation often needs to span multiple independent services. Consider an order placement. It might involve debiting a customer's account payment service, allocating inventory service, and creating a shipping request shipping service. If any of these steps fail, the entire operation should ideally be rolled back or compensated for to maintain data integrity. This is the challenge of a distributed transaction. Traditional two-phase commit protocols, common in monolithic systems, are generally avoided in modern distributed architectures due to their tightly coupled, blocking nature. Sagas provide a pattern to manage these complex distributed transactions, ensuring atomicity, all or nothing, across multiple services using a sequence of local, atomic transactions, with a mechanism for compensating for failures. Definition: a saga is a sequence of local transactions, where each local transaction updates the state within a single service and publishes an event that triggers the next step in the saga. If a local transaction fails, the saga executes a series of compensating transactions to undo the changes made by previous successful transactions. The problem it solves: it achieves atomicity and consistency across multiple services without relying on tightly coupled, blocking distributed transactions. It embraces eventual consistency, ensuring that eventually, either all parts of the business process succeed or all are consistently rolled back. How it works: two main ways to implement sagas. Choreography-based saga. Each service participates by executing its local transaction and then publishing an event indicating its outcome. Other services subscribe to these events, then perform their next action. If a service fails its local transaction, it publishes a compensating event, triggering other services to reverse their previously completed actions. Analogy: in our flash mob, if one dancer trips, they immediately signal a reverse gesture, and others who see it undo their last few moves until cohesion is restored. Pros: maximum decoupling. No central point of failure for the saga itself. Cons: can be difficult to manage and debug, especially for complex sagas with many steps or nested compensation logic. The flow is implicit and spread across many services. Orchestration-based saga. A dedicated saga orchestrator service explicitly manages the sequence of steps. The orchestrator receives the initial request, then issues commands to participating services for each step. Each participating service executes its local transaction and reports its outcome, success or failure, back to the orchestrator via an event. The orchestrator then decides the next step based on the outcome, including triggering compensating commands if a step fails. Analogy: our orchestra conductor explicitly directs each section, and if a section makes a mistake, the conductor will direct the necessary retractions or corrections for the whole piece. Pros: clear visibility of the entire saga flow. Easier to manage complex business logic and compensation. Cons: the orchestrator can become a single point of failure, though mitigated by making the orchestrator itself robust and resilient. The orchestrator is central, which introduces a form of coupling between itself and the services it coordinates. Compensation: the critical part of a saga is the concept of a compensating transaction. If a step in the saga fails, the saga must ensure that any previously completed steps are undone or reversed, leaving the system in a consistent state. This might involve refunding a payment, releasing reserved inventory, or deleting a temporary record. Designing these compensation paths requires careful thought. Interplay of patterns. It's common to see these patterns used together. Event sourcing provides the authoritative, immutable history of state changes. CQRS provides efficient, optimized read models derived from that event history. Sagas leverage this event-driven backbone to coordinate complex business transactions across multiple, independent services, often using events from the event store to drive their progress and orchestrate compensation. A service might be a producer of events for an event-sourced entity, a consumer of events to update a CQRS red model, and a participant in a saga by responding to commands and emitting events indicating its local transaction outcome. Conclusion: mastering complexity with events. Event sourcing, CQRS, and sagas are not trivial patterns. They add significant complexity to your architecture. However, they also provide powerful solutions for scalability, resilience, auditing, and managing distributed data integrity that are simply not achievable with simpler architectures. They embody the core principles of EDA by treating events as first-class citizens, driving change, and serving as the ultimate source of truth. Implementing these patterns successfully requires deep understanding, careful design, and often a cultural shift within development teams. But for systems that demand high scalability, rigorous auditing, and robust handling of distributed business processes, mastering these advanced event-driven patterns is an invaluable capability. In the next chapter, we will delve into one of the most critical and often challenging aspects of building distributed systems, especially those using events: managing consistency and concurrency, given the asynchronous nature of EDA. The challenge of consistency: managing state in an event-driven world. Introduction: the illusion of instantaneous consistency. In the world of monolithic applications, consistency often felt like a given. When a user updated a record, the change was immediately visible to everyone because all operations typically access the same database, often within a single transaction. It was like changing a single book in a library. Everyone immediately saw the update. However, event-driven architecture, EDA, with its emphasis on decoupled services communicating asynchronously through events, shatters this illusion of global, instantaneous consistency. While EDA offers immense benefits in terms of scalability, resilience, and agility, it introduces nuances in how data consistency is managed. This chapter will delve into the critical concept of consistency in distributed systems, particularly the pervasive reality of eventual consistency, and explore the strategies and patterns to manage it effectively. Understanding consistency in distributed systems. When we talk about consistency in this context, we're generally referring to data consistency, ensuring that data across different parts of a distributed system accurately reflects the most up-to-date state. Strong consistency. In a strongly consistent system, once a write operation is confirmed, all subsequent read operations will immediately reflect that new data. If user A updates their profile and user B immediately views that profile, user B will see the updated version. This is the ideal, but it comes at a significant cost in a distributed environment. It often requires complex locking mechanisms, consensus protocols, and can severely impact performance and availability. Eventual consistency. This is a hallmark of many modern distributed systems, including those built with EDA. In an eventually consistent system, once a write operation occurs, it is guaranteed that, at some future point in time, all replicas or views of that data will converge and reflect the latest state. However, there's no guarantee as to when that convergence will happen. For a brief period, different parts of the system might see different versions of the data. To illustrate, consider an online retail order. When a customer clicks Place Order, the order service immediately creates an order-placed event. The system can instantly tell the customer, "Thank you, your order has been placed." But it might take a few moments for the inventory service to process the event and actually decrement stock, or for the shipping service to add the order to its manifest. During that brief window, the order is placed, but the inventory might not yet reflect the change. Eventually, it will. Why eventual consistency is inherent to EDA. Eventual consistency isn't a flaw in EDA. It's a direct consequence of its design principles. Asynchronous communication. Events are processed in the background, out of band from the initial action. There's no blocking wait for all downstream services to complete their tasks. Decoupled services. Each service acts independently, reacting to events. They typically manage their own data store, meaning data is replicated and synchronized across different domains. Distributed nature. Data is spread across multiple services and potentially multiple databases, making instantaneous, global consistency computationally expensive or even impossible without sacrificing other desirable properties like availability and partition tolerance. As per the CAP theorem, strategies for managing eventual consistency. While strong global consistency is often impractical, the eventual part needs careful management. Users and business processes expect a coherent experience. Here are key strategies. Designing for user experience. Immediate feedback. Provide users with an immediate confirmation that their action was received, even if it hasn't been fully processed by all downstream systems. Your order has been placed. Optimistic updates. In some cases, you can immediately update the user interface with the expected outcome, assuming the backend operation will succeed. If it fails, you then roll back the UI, e.g., showing a like count immediately incremented before the server confirms. Displaying stale data with indicators. Inform the user when data might be slightly out of date. For instance, a stock indicator. Availability will be confirmed shortly. Or a refresh button for a dashboard. Pending or processing states. Use clear visual cues to show that an operation is underway and its final state will be consistent eventually. Technical patterns and mechanisms. Idempotency revisited. As discussed, consumers must be idempotent. In an eventually consistent system, messages can be duplicated or resent due to network retries or failures. An idempotent consumer will produce the same result regardless of how many times it processes the same event, preventing erroneous duplicate actions, e.g., crediting an account twice. Message ordering guarantees. For operations where the sequence of events is crucial, e.g., account debited before account credited. Using an event broker that guarantees message ordering within a partition, like Kafka, is vital. This ensures that even if processing takes time, the correct sequence of events is eventually applied. Retries and dead letter queues. Failure is inevitable in distributed systems. Consumers should implement robust retry mechanisms for transient errors. For persistent failures, e.g., malformed messages, events should be moved to a dead letter queue for manual inspection and debugging, preventing them from blocking the queue. Compensating actions, sagas. For complex business processes that span multiple services, if one step fails, you need a mechanism to undo or compensate for previous successful steps to maintain overall consistency. Sagas, as detailed in Chapter 5, are the primary pattern for this, embracing eventual consistency by ensuring that the final outcome is consistent. Either all steps complete or all are effectively rolled back. Consistency in read models. CQRS perspective. With CQRS, the read model is inherently eventually consistent with the write model. The challenge is ensuring the read model is updated quickly enough for user expectations. Materialized views. The read models are essentially materialized views of the events from the event store. They need to be updated efficiently and reliably. Projections. Services constantly project events into these read models. Monitoring the lag between the latest event and the processed event in the read model is crucial, e.g., how many events behind is the reporting database. Dealing with concurrency and conflicts. In distributed systems, especially with eventual consistency, what happens if two users try to update the same piece of data at almost the same time? Without centralized locking, conflicts can arise. Optimistic concurrency control, OCC. This is a common approach in eventually consistent systems. Instead of locking data proactively, you assume conflicts are rare. When reading data, you also record its version, e.g., a timestamp or a version number. When writing, you include the version you read. The write operation only succeeds if the data's current version matches the version you read. If not, it means someone else updated the data in the interim, and your write is rejected, requiring you to fetch the latest version and retry. Example: two users try to claim the last item in stock. Both read a quantity of 1. User A tries to buy, version matches, stock becomes 0. User B tries to buy, version doesn't match, transaction fails, user B is told the item is out of stock. Conflict resolution. For scenarios where rejecting a write is not an option, e.g., merging changes from multiple offline devices, you may need explicit conflict resolution strategies. Last right wins. Simply accept the most recent change. Simplest but can lead to data loss. Merge conflict. Automated or manual merging of changes, e.g., Git-style conflict resolution. Business logic. Apply specific business rules to resolve the conflict, e.g., for concurrent bids on an item, the highest bid wins. The importance of observability. Managing consistency in asynchronous, distributed systems is complex. Understanding why something is eventually consistent when consistency issues arose and where a problem occurred is paramount. Distributed tracing. Tools that trace a single request or business transaction across multiple services, spanning event publications and consumptions, are invaluable. They allow you to visualize the entire flow, identify bottlenecks, and pinpoint where eventual consistency might be causing issues. Centralized logging and metrics. Aggregating logs from all services and monitoring key metrics, e.g., event processing lag, error rates in consumers, provides crucial insights into the health and consistency of your system. Business transaction monitoring. Focus on monitoring the end-to-end completion of business processes, not just individual service health. Ensure that a placed order eventually results in a shipped order, and alert if these expectations aren't met within a predefined timeframe. Conclusion: embracing the asynchronous nature. Moving from a tightly coupled, synchronously consistent world to an event-driven architecture is a paradigm shift. It requires embracing eventual consistency as a fundamental reality and designing your systems and even your user experiences with this in mind. While it introduces challenges related to data freshness and concurrent updates, the benefits of scalability, resilience, and agility often outweigh these complexities. By strategically applying patterns like idempotency, comprehensive error handling, optimistic concurrency control, and relying on robust observability, you can build powerful and reliable event-driven systems that deliver a consistent and predictable experience to your users, even in the face of inherently distributed data. In the next chapter, we'll shift our focus from these architectural patterns to the practical considerations of implementing EDA, exploring choice of technologies and common pitfalls to avoid. Implementing EDA. Choosing technologies and overcoming obstacles. Introduction, bridging theory and practice. So far, we've navigated the theoretical landscape of event-driven architecture, EDA. We've understood its power, dissected the anatomy of an event, explored the core components, delved into advanced patterns, and wrestled with the nuanced challenge of consistency. These are the blueprints. Now it's time to build. Implementing EDA in the real world is where the rubber meets the road. It involves making concrete technology choices and confronting practical hurdles that can be both technical and organizational. While the benefits of EDA are compelling, achieving them requires careful planning, disciplined execution, and a proactive approach to common pitfalls. This chapter will guide you through the process of selecting the right tools for your event-driven toolkit and offer strategies for overcoming the inevitable obstacles you'll encounter on your journey. Key technological choices for your event-driven ecosystem. The beauty of EDA is that it's a paradigm, not a prescriptive set of technologies. Many tools can fit the various roles. Your choices will depend on your specific needs, existing infrastructure, team expertise, and budget. The event broker, the central hub. As discussed in Chapter 3, the event broker is the crucial intermediary connecting producers and consumers. Your choice here significantly impacts scalability, durability, and operational complexity. Distributed log systems, e.g., Apache Kafka, Apache Pulsar. These are highly scalable, fault-tolerant platforms designed to handle massive volumes of events as a persistent, ordered log. They are often chosen for use cases requiring strong ordering guarantees, high throughput, and the ability to reread historical event streams. They come with a rich ecosystem of connectors and tooling. Traditional message queues, e.g., RabbitMQ, Apache ActiveMQ. These are excellent for basic message passing patterns, particularly for point-to-point communication or simpler publish-subscribe models, where events might not need to be stored indefinitely. They often offer more advanced routing capabilities and can be simpler to operate for smaller scale needs. Cloud managed services, e.g., AWS Kinesis SNS SQS, Azure Event Hub Service Bus, Google Cloud Pub Sub. These services leverage the underlying cloud provider's infrastructure, handling much of the operational burden, scaling, patching, maintenance for you. They often seamlessly integrate with other cloud services and can be a cost-effective choice, especially for those already in a cloud environment. Factors to consider. Think about the required throughput, message retention period, ordering semantics. Are strict per partition orders sufficient, or do you need global order? Durability guarantees, and your team's familiarity with operating such systems. Event stores for event sourcing. If you've decided to adopt event sourcing, Chapter 5, you'll need a robust event store. Dedicated event store databases, e.g., Event Store DB. These are purpose-built databases optimized for storing and querying event streams, often offering features like projections and subscriptions out of the box. Distributed logs as event stores, e.g., Apache Kafka. With its durable, ordered log capabilities, Kafka is often used as the authoritative event store in conjunction with stream processing tools to build read models. Standard databases, with caveats. While possible to implement an event store on a relational or NoSQL database, directly managing event ordering, append-only constraints, and efficient query for projections can be challenging without dedicated tooling. Read model databases for CQRS. For the red side of CQRS, you gain significant flexibility. You can choose the best database for your specific query patterns. Relational databases, PostgreSQL, MySQL, good for structured data and complex joins. NoSQL databases, Cassandra, MongoDB, DynamoDB. Excellent for scalability, flexible schemas, and certain access patterns. Search engines, Elasticsearch, Apache Solr, ideal for full-text search, complex filtering, and analytical queries. Graph databases, Neo4j. Perfect for highly connected data where relationships are paramount. Serialization formats, the events language. Events, as they travel between services, need a common language. JSON. Widely adopted, human-readable, and flexible. Great for quick development and diverse consumers. Apache Avro, a compact binary format with a schema. Offers very strong schema evolution capabilities and good performance, often used with schema registries to manage compatibility. Google Protocol Buffers, Protobuf, another efficient binary serialization format that uses proto files to define messages. Known for forward and backward compatibility. Factors to consider. The balance between human readability for debugging, payload size, performance, and most importantly, robust schema evolution capabilities. Avro and Protobuf excel in managing schema changes over time. Common implementation obstacles and how to overcome them. No architectural pattern is without its challenges. EDA introduces its own set of complexities, but many have well-established solutions. Event schema management and evolution. The problem? Your events are your contracts. What happens when you need to add a new field to an order-placed event or change an existing one? Older consumers, or even newer ones that haven't been updated yet, might break, or new fields might be ignored by older services. Solutions: version all events. Include a version number in your event metadata, e.g., order placed v1, order placed v2. Be backward and forward compatible. Backward compatible. New consumers should be able to read old event versions. Forward compatible. Old consumers should be able to ignore new fields in newer event versions without crashing. This is why always adding optional fields is safer than removing or renaming existing ones. Schema registry. Use a centralized schema registry, often integrated with systems like Kafka, to define and manage event schemas. This provides a single source of truth and tools to check compatibility. Big bang changes are rare. Avoid making breaking changes without careful coordination. Often, it's better to publish a new event type, e.g., order checked out v2 alongside order checked out v1, and incrementally migrate producers and consumers. Error handling and retries. The problem? In asynchronous, distributed systems, failures are a given. A consumer might fail to process an event due to network issues, a downstream service being down, or a bug. If the event is simply dropped, data can be lost. Solutions: idempotency reiterated. Design consumers to be idempotent as discussed in Chapter 2 and 6. This is your primary defense against duplicate processing that can occur due to retries. Retry mechanisms. Consumers should automatically retry transient failures with exponential backoff, trying again after increasing delays. Dead letter queues, DLQs. For events that consistently fail after multiple retries, e.g., due to data validation errors or persistent bugs, move them to a DLQ for manual inspection and eventual reprocessing. This prevents a poison pill message from continually blocking a consumer. Circuit breakers. Implement circuit breakers in consumers to prevent continuous calls to a failing downstream service, allowing it time to recover and preventing resource exhaustion. Monitoring and observability. The problem? Debugging a synchronously failing monolith is complex. Debugging an asynchronous flow across dozens of services is exponentially harder. You can't just trace a single request through a debugger. Events can get lost in the flow, or processing delays can go unnoticed. Solutions: distributed tracing. Implement a distributed tracing system, e.g., OpenTelemetry, Jaeger, Zipkin. Inject a unique trace ID into every event's metadata when it's produced. As events flow through consumers and trigger new events or actions, propagate this trace ID. This allows you to visualize the entire end-to-end flow of a business operation across multiple services and message brokers. Centralized logging. Aggregate logs from all services into a centralized system, e.g., Elk Stack, Splunk, Datadog. Ensure logs include event IDs, trace IDs, and correlation IDs for Saga processes. Metrics and dashboards. Collect key metrics from producers, event publishing rate, brokers, message queues, consumer lag, and consumers' processing rate, error rate, processing duration. Monitor consumer lag, the indication of how many events a consumer is behind the latest event to ensure read models are fresh and processes are caught up. Business process monitoring. Create dashboards that show the progress of critical business processes, e.g., number of orders started versus number of orders fulfilled, not just technical system health. Data consistency challenges, managing eventual consistency. The problem? As explored in Chapter 6, eventual consistency is a fundamental reality. How do you ensure data integrity and avoid displaying stale data when it matters? Solutions: user experience design, as discussed in Chapter 6. Set appropriate expectations by showing, pending, states, or providing immediate confirmation and then updating later. Transactional outbox pattern. This is a crucial pattern for ensuring atomicity between a service's internal database changes and its event publications. Instead of publishing an event directly after modifying its database, the service writes the event to an outbox table within the same database transaction as the data change. A separate process then asynchronously reads from this outbox table and publishes the events to the broker. This guarantees that either both the database change and the event publication happen, or neither does, preventing data inconsistencies. Testing event-driven systems. The problem: testing asynchronous, distributed interactions can be complex. Unit tests are insufficient for verifying end-to-end behavior. Solutions: unit tests. For individual components and business logic within services. Integration tests. Test the interaction of a service with its immediate dependencies, like the event broker. This might involve setting up a lightweight in-memory broker for local testing. End-to-end, E2E, tests. Simulate full business processes by sending an initial event and asserting that the expected final state or series of events occur. These are usually slower and more complex to set up. Consumer contract tests. Ensure that consumers correctly define their expectations of event schemas and producers correctly fulfill those contracts. This prevents breaking changes between services. Organizational and cultural shift. The problem: moving to EDA fundamentally changes how development teams interact. From shared database schemas to independent services, it requires new ways of thinking and collaborating. Solutions: More in Chapter 9, foster cross-team communication, educate developers on event-driven principles, empower teams with autonomy over their services and data, and ensure clear ownership of event contracts. Best practices for implementation. Start small. Don't try to migrate your entire monolith to EDA overnight. Identify a small, non-critical, but representative use case to experiment with and learn from. Design for idempotency from day one. Don't treat it as an afterthought. It's fundamental for resilience. Establish clear event contracts. Document your events rigorously. This includes schema, purpose, and examples. Treat events as immutable APIs. Prioritize observability. Invest in distributed tracing, centralized logging, and comprehensive metrics from the beginning. You cannot manage what you cannot see. Smart events, dumb consumers. Events should carry enough context that consumers don't need to make immediate synchronous calls back to the producer to get more data. This maximizes decoupling. Consider Conway's Law. Align your team structures with your proposed service boundaries. Autonomous teams are better equipped to build and maintain autonomous services. Conclusion: the discipline of distributed systems, implementing event-driven architecture, is a journey that demands discipline and a shift in mindset. It forces you to confront the inherent complexities of distributed systems, particularly around data consistency and communication. However, by carefully selecting the right technologies, proactively tackling common obstacles, and adhering to best practices, you can successfully build highly scalable, resilient, and adaptable systems that truly respond to the dynamic nature of modern business. In the next chapter, we will ground these concepts further by exploring real-world applications where EDA truly shines, demonstrating its power in diverse industries. Real-world applications, where EDA shines brightest. Introduction: from theory to transformative impact. We've explored the foundational principles, architectural patterns, and implementation challenges of event-driven architecture, EDA. We've seen how events become the language of communication between decoupled services, enabling scalability, resilience, and agility. But what does this look like in practice? Where is EDA making a tangible difference in the real world, and what kinds of problems does it solve most effectively? This chapter will move from the theoretical to the practical, showcasing compelling use cases and industries where EDA has become a transformative force. While nearly any domain can benefit from aspects of EDA, certain scenarios particularly highlight its strengths and demonstrate its ability to handle high-throughput, complex business processes and evolving requirements. 1. E-commerce and retail, the customer journey in real time. One of the most natural fits for EDA is the e-commerce landscape, characterized by peak traffic, complex customer journeys, and the need for immediate, personalized responses. Use case: order processing and fulfillment. Challenge: a customer places an order. This single act triggers a cascade of necessary, but independent, actions: processing payment, updating inventory, sending order confirmation emails, notifying the warehouse, calculating shipping costs, and updating customer loyalty points. In a traditional synchronous system, a single failure could halt the entire process or make the customer wait. During peak sales, e.g. Black Friday, the system must handle immense, unpredictable loads. EDA solution: when order-placed event occurs, the order service publishes it to the event broker. The payment service consumes it to process payment, publishing payment processed or payment failed. The inventory service consumes order placed to decrement stock, publishing inventory updated or out of stock. The notification service consumes order placed and later payment processed, order shipped, etc., to send customer updates. The shipping service consumes order placed and often inventory updated and payment processed to initiate fulfillment. The loyalty service consumes order placed to award points. Impact: massive scalability for order intake, improved resilience. If payment fails, inventory update still proceeds, and the customer is notified of the payment issue. Ability to easily add new features, e.g., fraud detection, personalized recommendations, by simply subscribing to existing events without modifying core systems. Customers get immediate feedback, even if backend processing takes time. Use case: personalization and customer experience. Challenge: reacting to real-time customer behavior to offer relevant product recommendations, dynamic pricing, or targeted promotions. EDA solution. Events like product viewed, item added to cart, search performed, and login attempt are streamed continuously. Machine learning services consume these events to update user profiles, personalize content, and trigger contextual offers. Impact, highly responsive and personalized user experiences, increased engagement and conversion rates. 2. Financial services, real-time transactions, and regulatory compliance. The financial sector benefits immensely from EDA due to the need for high transaction throughput, immutability, auditability, and fraud detection. Use case, payment processing and fraud detection. Challenge, tens of thousands of transactions per second, low latency requirements, and the critical need to identify and prevent fraudulent activity in real time. EDA solution. Every transaction is an event. Transaction attempted, payment authorized, fund transferred. These events are streamed to an event broker. A fraud detection service consumes transaction attempted events, applies real-time analytics and machine learning models, and publishes fraud detected or transaction flagged events. Downstream systems consume payment authorized to update account balances. Impact, near real-time fraud detection, high throughput for payment networks, creation of an immutable audit trail for every financial event, simplified compliance and reconciliation. Anecdote, many large payment processors use event streaming platforms like Kafka to handle the staggering volume of transactions, recognizing that events are the most truthful and direct representation of financial activity. Use case, trading systems. Challenge, processing market data updates, order submissions, and trade executions with extremely low latency, ensuring fairness and auditability. EDA solution. Market data feeds, order placement requests, trade confirmations, all are events. A trading system might capture price quote updated, order submitted, trade executed events. Algorithmic trading engines consume these events to make split-second decisions. Impact, real-time responsiveness to market conditions, ability to build complex trading strategies, robust audit logs for regulatory scrutiny. 3. Internet of Things, IoT, ingesting and reacting to sensor data. IoT generates massive volumes of time series, data from sensors, devices, and machines. EDA is perfectly suited for managing this torrent of information. Use case, smart homes, cities, and industrial IoT challenge, ingesting data from millions of devices, temperature sensors, smart meters, motion detectors, and reacting to anomalies or desired states in real time. EDA solution, every sensor reading, temperature reading, door opened, machine vibration is an event. A central data ingestion pipeline using an event broker like Kafka captures these events. Analytics services consume these events to detect anomalies, e.g., sudden temperature drop in a freezer, trigger alerts, e.g., fire alarm triggered, or automate actions, e.g., lights on. Predictive maintenance systems can use historical event data to anticipate equipment failures. Impact, scalable ingestion of massive data volumes, real-time reactions and automation, proactive maintenance, enhance safety and efficiency. Case study, companies managing large fleets of vehicles, tracking deliveries, or optimizing logistics use highly event-driven architectures to process location updates, delivery status changes, and vehicle diagnostics, enabling real-time rerouting, customer notifications, and preventative maintenance. 4. Healthcare, integrating disparate systems and patient monitoring. Healthcare systems are complex, often fragmented, and require stringent data integrity and privacy. EDA offers a powerful integration fabric. Use case, electronic health records, EHR integration. Challenge, integrating diverse systems, hospital management, lab results, pharmacy, billing that may use different technologies and data formats, ensuring patient data is updated consistently across systems. EDA solution, critical patient events, patient admitted, lab result available, medication prescribed, diagnosis updated, are published. Middleware services consume these to update respective systems dynamically. Impact, improved data flow and accessibility across different healthcare applications, leading to better patient care coordination, reduced errors, and more streamlined administrative processes. Use case: remote patient monitoring. Challenge: monitoring vital signs from wearables or home devices to detect emergencies or health deterioration, triggering alerts for caregivers. EDA solution: heart rate, glucose levels, activity data are streamed as events. Real-time correlation engines consume these to identify critical patterns: heart rate spike, glucose level low, generating emergency alert events for medical personnel. Impact: proactive healthcare intervention, enabling care for patients at home, reducing hospital readmissions. 5. Data engineering and analytics, real-time data pipelines. One of EDA's most profound impacts is on how organizations manage and process their data, shifting from batch processing to real-time stream processing. Use case: building real-time data warehouses and analytics dashboards. Challenge: traditional data warehousing involves ETL, extract, transform, load processes that run in batches, meaning reports are always hours or days old. Modern businesses demand real-time insights. EDA solution: all operational changes are captured as events, e.g., product updated, customer created, page visited. These events form a continuous stream. Data transformation services consume these events, process them in real time, and load them into analytical data stores or real-time dashboards. Impact: up-to-the-minute business intelligence, allowing faster decision-making, enabling reactive adjustments to marketing campaigns, sales strategies, or operational processes. Conclusion: the pervasiveness of events. These examples merely scratch the surface of EDA's applicability. From gaming leaderboards to supply chain logistics, from telecom network management to content delivery, the pattern of something happened and now other systems need to react is universal. The true power of EDA lies in its ability to model the world as a series of immutable facts, events, and build systems that are inherently reactive, highly scalable, and exceptionally resilient. It fosters an architecture where adding new capabilities simply means subscribing to existing events, leading to a much more agile and adaptable enterprise. While not suitable for every single problem, for domains characterized by high throughput, complex asynchronous workflows, the need for real-time responsiveness, and stringent audit trails, event-driven architecture is not just an option. It's often the paradigm of choice for building the next generation of scalable and robust systems. In our next chapter, we will shift focus from the technical implications to the broader organizational and strategic aspects of adopting EDA, recognizing that technology is only one piece of the puzzle. Adopting EDA. Beyond technology to culture and strategy. Introduction: the unseen layers of architectural chain. Throughout this book, we've dissected event-driven architecture, EDA, from its fundamental concepts to its advanced patterns and practical implementation. We've explored the what and how of events, producers, consumers, brokers, and the challenging world of distributed consistency. However, implementing EDA successfully involves far more than merely choosing the right broker software or mastering the intricacies of eventual consistency. Just like a ship needs a skilled crew and a clear shared vision to navigate, a technical architecture needs an aligned organizational culture and a thoughtful strategy to truly set sail. Adopting EDA is not just a technological deployment. It's a fundamental shift in how teams operate, how they communicate, and how they collectively think about data flows and business processes. It impacts everything from team structure and collaboration models to debugging processes and strategic road mapping. Ignoring these organizational and cultural dimensions is a common pitfall that can undermine even the most technically sound EDA design. The cultural shift, embracing a new paradigm. At its core, EDA encourages a mindset fundamentally different from traditional monolithic or rigidly synchronous architectures. This shift requires a conscious effort from everyone involved, from synchronous to asynchronous thinking. For years, developers have been trained to think in terms of linear, synchronous flows. Call A, wait for response, then call B. EDA demands a reactive, asynchronous mindset. Something happened, and now various parties can react independently. This means accepting the reality of eventual consistency at a core level. Product managers need to understand that a user action might not trigger an instantaneous global update across all systems. Business stakeholders must be informed about the implications of this delay, e.g., your order has been placed. You will receive a shipping confirmation email within the next hour. From centralized control to decentralized ownership. Monolithic systems often foster centralized ownership, where a single team or department is responsible for a large chunk of functionality, often leading to bottlenecks. EDA, with its decoupled services, pushes authority and decision-making down to individual, autonomous teams. Each team should own its services, including the events they produce and consume. This move empowers teams but requires trust and clear boundaries. From direct commands to reactive listening, the shift from "I tell you what to do" commands to "I announce what happened" events requires a new form of communication. Developers must learn to model business processes not as direct orchestrations, but as sequences of facts that other services can then interpret and react to. This fosters a more resilient and extensible system, but also a more indirect communication paradigm that takes getting used to. Embracing failure as a given. In synchronous systems, a failing dependency often means the entire upstream transaction fails immediately. In EDA, with its emphasis on queues and retries, individual service failures typically don't cascade instantly. This means designing for resilience becomes paramount, accepting that components will inevitably fail, and focusing on how the system recovers and self-heals rather than simply trying to prevent all failures. Organizational impact and team structures. The structure of your organization inevitably influences the architecture of your systems. This phenomenon is often summarized by Conway's Law. Organizations which design systems are constrained to produce designs which are copies of the communication structures of these organizations. Autonomous cross-functional teams. EDA thrives when development teams are structured to be cross-functional, including developers, testers, product owners, operations specialists, and autonomous, meaning they own their services end-to-end, from conception through development, deployment, and operation, including the events they generate and consume. This aligns perfectly with the decoupled nature of EDA, where specific teams can own specific bounded contexts. Breaking down silos. A successful EDA implementation requires breaking down traditional silos between front-end, back-end, data, and operations teams. Events become the common language, and often, a front-end team might directly consume events, or a data analytics team might leverage the same event streams as operational services. This necessitates increased cross-team communication and collaboration. Shared understanding and domain-driven design. For events to be truly meaningful across different services, a shared understanding of the business domain is crucial. Techniques like event storming collaborative workshops, where business and technical experts map out events and aggregates, are invaluable for explicitly defining events, identifying service boundaries, and ensuring everyone speaks the same, ubiquitous language about the key occurrences in the business. Strategic adoption, how and where to start. Given the cultural and technical shifts, a big bang migration to EDA is rarely advisable. A strategic, incremental approach is usually best. Start small, learn fast. Don't attempt to rewrite your entire monolithic application. Identify a small, contained, ideally greenfield project or a clearly defined bounded context within an existing system. This low-risk environment allows your teams to experiment, learn the new patterns and tools, and develop the necessary muscles without paralyzing critical business operations. Identify good candidates. Look for areas where EDA offers clear, immediate benefits. These often include high-throughput processes where traditional synchronous scaling is challenging, complex asynchronous workflows where coordination across multiple, independent steps is needed, e.g., order fulfillment, loan processing, data integration needs, where disparate systems need to share information without tight coupling, auditability and temporal analysis, where a full history of changes is critical, e.g., financial transactions, compliance. Refer back to Chapter 8's use cases for inspiration. Pilot projects and internal champions. Choose a visible project that, if successful, can demonstrate the value of EDA to the broader organization. Cultivate internal champions, developers, architects, and product managers who are enthusiastic about EDA and can evangelize its benefits, mentor others, and overcome resistance. Consider incremental migration. For existing systems, identify seam points where you can introduce events. For example, replacing a direct API call between two internal services with an event-driven integration, or using a transactional outbox pattern to publish events from changes in your existing database. See Chapter 7. Governance and collaboration in an event-driven world. Decentralization doesn't mean chaos. In an event-driven world, clear governance is critical to ensure interoperability and avoid a wild west of ad hoc event definitions. Event Contract Catalog Registry. This is paramount. Establish a centralized, accessible repository where all events produced in your organization, their schemas, definitions, purpose, ownership, and examples are formally documented and versioned. Tools like schema registries, often used with Kafka or OpenAPI specifications, for API-driven commands queries, play a vital role here. This ensures that any team can discover and understand existing events. Strict versioning policies for events. Treat event definitions as immutable API contracts. Establish clear policies for schema evolution, e.g., always additive, no breaking changes. If breaking changes are necessary, publish a new major version of the event. This is a critical discipline for backward and forward compatibility, as detailed in Chapter 7. Shared tooling and best practices. While teams are autonomous, a central platform or architecture team can provide common infrastructure and guidelines for using event brokers, observability tools, distributed tracing, centralized logging, and common development patterns. This accelerates adoption, ensures consistency, and reduces operational overhead for individual teams. Federated ownership with central guidance. The ideal balance is to empower teams to own their events and services while providing architectural guidance and a shared platform to ensure consistency, discoverability, and interoperability across the organization. Skills development and continuous learning. Adopting EDA requires new skills, not just technical, but also in terms of system thinking and collaboration. Technical upskilling. Teams need training in using the selected event broker, understanding stream processing concepts, implementing idempotency and error handling, and leveraging distributed tracing tools. Proficiency in different database types for CQRS read models might also be necessary. Architectural guidance. There's a strong need for experienced architects who understand the nuances of distributed systems, can guide teams through complex event modeling, arbitrate design decisions, and ensure architectural consistency across the organization. New problem solving. Debugging in asynchronous environments often means learning new techniques and tools. Reproducing issues or understanding state might require replaying events from a log. Conclusion. The journey, not the destination. Adopting event-driven architecture is significant organizational change. It's a journey that demands patience, continuous learning, and a willingness to adapt. It requires acknowledging that people and processes are as crucial as the technology itself. By fostering a culture that embraces asynchronous thinking, decentralized ownership, and robust communication, by strategically identifying pilot projects, and by investing in event governance and skill development, organizations can navigate this transition successfully. When implemented thoughtfully, EDA becomes a powerful catalyst for innovation, enabling businesses to build systems that are not only faster and more scalable, but fundamentally more resilient and responsive to the ever-accelerating pace of the digital world. The future belongs to those who can master the art of reacting to what's happening in real time. The future of systems, event-driven everything. Introduction. Looking beyond the horizon. We've journeyed through the intricacies of event-driven architecture, EDA. From its foundational concepts to its advanced patterns, practical implementations, and the crucial organizational shifts required for successful adoption. We've seen how events serve as the lifeblood of modern systems, enabling unparalleled scalability, resilience, and agility. But what does the future hold for this paradigm? Is event-driven everything, an inevitable reality, a utopian ideal, or an overzealous technologist's dream? In this concluding chapter, we will peer into the future, exploring the ongoing evolution of EDA, its growing convergence with other technologies, and its potential to reshape how we build and interact with software systems. We'll consider the promise of a fully reactive enterprise, potential challenges on the horizon, and the enduring value of understanding event streams. The expanding horizon of event-driven principles. EDA is not a static concept. It's a continuously evolving architectural style. Several trends indicate its increasing pervasiveness. Event streaming as the digital nervous system. Platforms like Apache Kafka and Apache Pulsar have moved beyond mere message brokers to become full-fledged event streaming platforms. They are increasingly seen as the central nervous system of modern enterprises, capturing all significant business events in real time. This provides a single, unified, immutable source of truth for operational systems, analytical systems, and audit trails. The idea of an enterprise event bus that truly encapsulates all organizational activity is gaining traction. Convergence with data analytics and machine learning. The line between operational systems and data analytics is blurring. With events as the common currency, the same event streams that power your e-commerce operations can directly feed real-time analytics dashboards, fraud detection models, and personalized recommendation engines. This enables data to be actionable as it happens, fostering a truly data-driven organization. Concepts such as feature stores, which use events to build and serve data features for machine learning models, are a testament to this convergence. Event-driven microservices as the default. While not every microservice needs to be purely event-driven, the benefits of asynchronous communication and decoupling provided by events are making it a default communication pattern in many microservice architectures. This is driven by the desire for greater autonomy for teams and more robust, scalable deployments. Rise of low-code, no-code event-driven platforms. As EDA matures, we're seeing the emergence of platforms that abstract away much of the underlying complexity, allowing business users or citizen developers to define event-driven workflows and integrations without extensive coding. This democratizes the power of reactivity, bringing its benefits to a wider audience. Event-driven APIs and API gateways. The external face of your system, the API, is also evolving. Event-driven APIs, e.g., webhooks and server-sent events, allow external systems to subscribe to internal events, providing real-time data push rather than constant polling. API gateways are also becoming more event-aware, facilitating sophisticated routing and transformation of event streams. Beyond traditional business applications. New frontiers. The principles of EDA are finding application in diverse and emerging fields. Decentralized finance, DeFi, and blockchain. Blockchain technologies are inherently event-driven, with each block representing a set of immutable events, transactions. Smart contracts react to these on-chain events. This is arguably the ultimate form of a globally distributed, eventually consistent, event-sourced system. As DeFi grows, understanding event stream processing, e.g., for real-time analytics of blockchain transactions, becomes critical. Digital twins and the metaverse. Creating high-fidelity digital replicas of physical assets or environments, digital twins, requires consuming real-time events from physical sensors and systems. These events then update the digital twin, which in turn can publish its own events to trigger actions or simulations. The immersive, interactive nature of future metaverse applications will undoubtedly rely heavily on real-time event processing for responsiveness and synchronization. Event-driven security. From detecting anomalies in user behavior to tracking the provenance of data and software, security is increasingly adopting event-driven patterns. Security information and event management, SIEM, systems are essentially large-scale event consumers, analyzing security events for threats. Autonomous systems. Self-driving cars, drone swarms, and intelligent robots all operate by sensing their environment events, processing that information, making decisions, and executing actions. Their entire operational loop is fundamentally event-driven, often requiring ultra-low latency event processing at the edge. Challenges on the road ahead. Despite its immense potential, the journey towards event-driven everything is not without its hurdles. Complexity management. As systems become more distributed and reliant on events, managing their complexity remains a significant challenge. The overhead of tooling for distributed tracing, schema management, and ensuring end-to-end consistency can be substantial. Talent gap. A deep understanding of distributed systems, eventual consistency, and event-driven patterns is still a specialized skill. The demand for engineers and architects proficient in these areas will continue to outpace supply. Cultural inertia. Organizations deeply entrenched in traditional, synchronous ways of working will continue to find the transition challenging, requiring sustained leadership and education. Cost of infrastructure. While cloud services simplify operations, robust event streaming and storage platforms can still incur significant costs at scale. Data governance and privacy. As events flow freely and widely across an enterprise, ensuring data governance, privacy compliance, e.g., GDPR, CCPA, and security becomes even more complex, requiring careful consideration of what data is propagated in events and how it's handled. The enduring value of event streams. Regardless of specific technology trends, the core value proposition of EDA modeling the world as a series of immutable facts is profound and enduring. A single source of truth. Events provide the most direct, unvarnished history of your business. They are the objective facts. Unlockable business value. By capturing every meaningful occurrence as an event, organizations create a rich, replayable dataset that can be analyzed, replayed, and repurposed in countless ways, often unforeseen at the time the event was first produced. This data liquidity is a tremendous asset. Adaptability to change. When new business requirements emerge, an event-driven system is inherently more adaptable. Instead of retrofitting existing monolithic code bases or breaking tight dependencies, new services can simply subscribe to relevant events and react. Conclusion: a mindset for the future. Event-driven architecture is more than just an architectural pattern. It's a mindset. It encourages engineers, architects, and indeed, entire organizations to think differently about how systems interact, how data flows, and how business processes unfold. It's a shift from static, command-and-control structures to dynamic, reactive ecosystems. This book has aimed to provide you with the foundational knowledge and practical insights to navigate this exciting paradigm. Whether you're building a small, agile service or redesigning an entire enterprise, embracing event-driven principles will equip you to create systems that are not just technically sound, but truly resilient, scalable, and adaptable to the accelerating pace of change in our increasingly interconnected world. The future favors the reactive, and understanding events is your key to thriving in it.